We saw in the last video that we could actually find a direct relationship between the equilibrium constant, the thermodynamic equilibrium constant, and the standard cell potential given by this relationship here, where Z is the number of electrons that are transferred, or the moles of electrons that would be transferred in an oxidation reduction step. Now, what I want to do is show how in practice we can use this to find such things, say, as the solubility product equilibrium constant. Remember that corresponds if we have a substance, I'll call it MX, that is going to dissolve partially in water. It might form M ions and X ions. Okay, but the equilibrium lies far to the left. That is, it's sparingly soluble, and we want to get a handle on how soluble it can be, how much stuff can dissolve. So how would we use an electrochemical cell to get at this problem? Well, first of all, we may not be able to access this exact process, but there are a couple of other related processes that will help us get there. So let me draw a line underneath this to separate it, because what we're going to talk about underneath here is a little bit separate. All right, so you might have, for example, a process where you start with this salt as a solid and add electrons to it in an electrochemical process, and it would form an equilibrium with the metal part, M, as a solid, and ions involving the anion part, the X minus. Right, and this would have, for example, a standard reduction potential. I'll call it standard reduction potential 1. Then you might also have a process where you can easily measure the aqueous ions of this metal, in which I add an electron, and this would end up giving us the solid metal again. And I'll call this one E reduction 2. Okay, so these are two things that you might find listed in a standard reduction table. Okay, but what I want is this equation. So is there a way I can put these together to get that? Well, first of all, notice that this thing appears in only one of these two equations, and it's the first one. And it appears on the left-hand side, so it's already positioned correctly for this. All right, but this quantity appears only here, and it appears on the left side in the half-cell reaction, but we need to have it on the right-hand side. So in other words, I need to reverse this second half-cell reaction in order to make all of this work. And so what I'll really need is to find E oxidation for this step, and that's going to be equal to negative E reduction for this step. All right, so let's suppose that we're able to reverse this step and then add the two steps together. Okay, so another way of saying that is I could subtract the second step, if you will follow me. That means the electrons will cancel out, and since I'm subtracting, these will cancel out also, and this will move over to the other side. So the subtraction of these two chemical equations would give me this, which is in fact exactly the equation that I want. So subtracting these quantities means that the cell potential for this entire reaction would just be their difference. The reduction potential for 1 minus the reduction potential for 2. All right, so basically we found a way that we can combine these half-cell reactions so that we get the one that we're interested in, and then we would be able to determine our equilibrium constant for this process from this cell potential. So in other words, I would have that KSP is just equal to exponent of all of this stuff up here. So I'd have Z times the Faraday constant over RT times the cell potential. All right, so this gives us a really handy way of taking tabulated information, essentially, and turning it into a solubility product constant. So let's see how this works in practice. Let's suppose what we're interested in is the solubility of silver sulfate. Most sulfates are soluble. Silver sulfate turns out to be one of those that is an exception. So if I'm interested in the solubility of this, the reaction that I'm interested in is having this go to silver ions and sulfate ions, both in aqueous solution, and there's going to be 2 of the silver ions because there's a 2 down here. Okay, so how would I put this together? All right, well, first of all, you would either be given or you would find in a table that this material, silver sulfate, can be reduced, producing 2 silver solids, so it's a way of pulling silver out of it, and sulfate ion in aqueous solution. And this would have a reduction potential, okay, we'll call it ERED1, of 0.627 volts. Okay, we also know, though, that the silver itself can be reduced, silver ion can be reduced. Okay, silver ion presumably also in aqueous solution, to form silver metal solid. And that this reduction potential, and I'm quite positive that this one is listed in the table, has a value of 0.799 volts. Okay, but what we're going to need to do in order to get our desired reaction up here is to reverse this second reaction. Okay, so when we reverse this reaction, we'll end up with silver solid goes to silver ions in aqueous solution plus an electron. And that will cause this to be negative. So now when I put these together to get the reaction that I want up here, it means I'm going to add this reaction and this reaction. So I need to add those 2 cell potentials, or 2 half cell potentials. I will get the net reaction that I want here when I add these 2 together. And those are 2 silvers plus a sulfate. And when I do that, I'll find that the cell potential in this case is actually a negative cell potential. I'll get negative 0.172. That's the difference between this and this. All right, so immediately what that tells us is that this doesn't spontaneously happen, at least moving to the right, but we already knew that. This is a sparingly soluble salt. So that means that its equilibrium is going to favor the left-hand side. It's going to favor the non-dissolved silver sulfate. But we can still use this now to find the solubility product constant using this formula. So I would have that my KSP now is going to be given by the exponent. Okay, Z in this case, I need 2 of these silvers, so there's going to be 2 there, and there's 2 here, so Z is equal to 2. Faraday constant is this large number, and divided by R, which is going to be 8.314, and temperature 298, and then our cell potential is going to be negative 0.172. And I got my thing mixed up here. This is 96.485. Sorry about that. Better to get the Faraday constant correct. All right, so when we put all of these numbers in and we take the exponent of it, we would find that our solubility product constant is going to be 1.52 times 10 to the minus 6. All right, something that we can get entirely from this use of standardized reduction potentials for different quantities and a little bit of knowledge of how to apply the Nernst equation.